Today I'm going to talk about incidences between points and planes in real space. So let me talk about, first, let me start with incidences between points and lines in real space, which is a very classical subject in discrete geometry. The most important theorem in the area is the Semiretti-Trotter theorem. So this is from 1982 or so. It has two equivalent formulations. The first one is, it's given a set P of set P of points, and a set L of lines, both in the real plane. We're going to always keep M as the number of points and N as the number of lines. Then the number of incidences between the points and the lines is at most order m to the 2/3, n to the 2/3, plus m plus n. And probably most of you know this in notation, but I'm going to keep the notation on this board because later on there'll be some more complicated and less familiar notation, so it would be nice to just keep things. Given a set of points and some geometric objects, in this case lines, but later on higher dimensional flats, the incidences between the points and lines, this will be the number of pairs PL such that the point is contained in the line. So we have a point, we have a line. The incidence is the point of the line and is the pair of the point and the line such that the line is contained in the point. And there's an equivalent formulation of this theorem in terms of given a fixed set of points, how many lines are there that contain a large number of the points. So equivalently, and I like this f sub 1 for lines less than t. That's the number of lines that contain at least t greater than t, at least 2 points. And p is bounded above by m squared over t cubed plus m over t. This is a t, and this is a 1. This is a f. And in general, I'll write f sub k with some inequality up above. Well, that's the number of Kflats containing at least t points of p. So there's an implicit argument here that will whenever it's not obvious from the context, I'll put the argument in explicitly.
So the at least t there means you want at least t there as well, or is that specifically another inequality? Okay.
Yeah, you can put another inequality there, but this is going to be the most important one. So proving this inequality from this inequality is completely straightforward. You can just say, put in f of t for n here. The number of incidences is going to be at least t times the number of lines. And then you can just solve it, and this is what is going to come out. The other direction is a little bit more involved you need to break the lines up into those that contain fewer than the square root of the number of points, those that contain more. The lower part we can do a dyadic summation of for this part of this inequality, and for the upper part we need to use a Cauchy-Schwarz, a kind of trivial bound, just using the fact that you can't have a pair of points and two different lines that contain it. So this is a fact about the underlying graph structure that you can use to get a weaker incidence bound. It's worth noting that, this is a genuinely theorem about points and lines in the real plane. If you think about, if you happen to not be familiar with this theorem, but you are familiar with the projective plane, you can think about, if you take all of the points and all of the lines in a finite projective plane, it would give a counterexample to this theorem. For example, in FQ squared, you have roughly Q squared points, roughly Q squared lines. Every line is incident to Q points. So how many Q-rich lines should there be is at most Q to the fourth over Q cubed plus Q squared over Q is Q. But we know that there would be Q squared Q-rich lines. So this is really a theorem. The fact that the points and lines are in real space is critical for the theorem to be true. There's one other theorem, another classical theorem that I want to talk about. Let me put this up, actually. It was proved around the same time as Semmery and Trotter. It's Becks Theorem. And here we're saying the claim is that either the vast majority of the point, given a set of points in the plane, either the vast majority of the points lie on a single line, or the number of lines that span is at least n squared. So here, for spanned flats, I'm just going to put a F subscript. This should be M. So given a set of M points where no line contains more than G, the number of lines spans is at least M times N minus G. So the kind of picture is we have some line, and this here contains G points. We have maybe a few N minus G that don't lie on the line. And really the meat of this theorem is when G is fairly large. So we're saying when you have a quadratically large number of lines. In the case that almost all the points lie on a single line, well, each point that's not on that line can span, the first point that's not on the line can span G lines with the points on the line. And the second one is going to share at most one of these lines. So then you have G plus G minus 1 plus, which is going to give you order G times N minus G. And in the case that G is a substantial fraction of all the points, so most of the points are collinear and you just have a few off, then this very simple argument is going to give you this type of bound. So kind of the meat of the theorem is showing that if you have, say, square roots of M points on each line, then you have to have, you can't cover all the pairs of points with lines that each contain square roots of M points. Because if you manage to cover all the pairs of points with lines having square root of M points, well, each line covers M pairs. So you could cover all the distinct pairs with m such lines, but we have actually, in the case that G is small, this is giving us omega m squared. So again, this is something that's in general. If you forget about the fact that the points are contained in the real plane, and imagine they're contained in, say, a finite plane, or you just have an arbitrary set system, you really can't get anything better than m, or just the number of points here. And so we're really using the fact that the points are embedded in the real plane to get this bound. Now these are two classical theorems from the early 1980s. What I really want to talk about today is higher dimensional generalizations of these. The first one was proved by Beck at the same time that he proved this. He also proved a higher dimensional generalization. Oh, actually, before I talk about points and planes, let me just mention that both of the theorems that I mentioned don't need to be generalized at all to be applied in higher dimensions. If you're given a set of points and lines in, say, RD, instead of in the plane, you're now in a d-dimensional space. If you had more incidences than this number, then you can project this down into a plane and get that same number that you had in the higher dimensional space. So the fact that this theorem applies in the plane also implies it in the higher dimensional space. Similarly, here, if you're given an arrangement of lines and points, you're given some arrangement of points in space, and it determines some set of lines. When you project that, if you project that set of points down into a plane, you're only going to lose lines. You might have, so if I draw, here's three points, and I tell you, these are in some higher dimensional space. You can't tell looking at the picture whether this is giving you 3 lines or 1 line. They might all be collinear, or they may not be. But you're never going to have the opposite situation where in the higher dimensional space, everything is collinear, but then if you project it down into the plane, suddenly you're getting additional lines. So again, Beck's theorem in the plane immediately implies the same bound for points in the higher. It immediately implies that in some higher dimensional space, the number of lines spanned is still bounded below by this quantity. So there are ways to make questions about incidences and incidences between points and lines in higher dimensional space interesting, but you really need to apply some assumption that your underlying structure is genuinely higher dimensional, and that's not the direction that I want to take this talk. What I'm going to talk about today are incidences between higher dimensional planes and points. So here, Beck's theorem is for all k at least 1, there are positive constants c sub k prime such that either one. There's alternative 1 is a single Kflat contains c sub k times m points of P. The second alternative is that you span nearly as many K-flats as possible. So f sub k is omega, well, I've written the constant explicitly, ck prime times m to the k plus 1. So in terms of notation, I'm writing fk is the number of K-flat spans And what I mean when I say a K-flat is spanned by P is that you have K plus 1 points contained in the K-flat such that no K that don't lie on a lower dimensional space. Now, it's easiest, I won't really be talking too much about things about 3 dimensions, but you can think about in 3 dimensions, if you have 3 non-collinear lines, there's a unique plane that passes through these lines, and that's spanned by those 3 points. So you can start out with a point, you can talk about the span of a geometric set in space as the lowest dimensional affine subspace that contains those. And you can say that given a finite set of points, I say that a plane or a line or something like that is spanned by the set of the points if there's a subset of the points that spans exactly that space. So for lines, because it's easy to draw, being spanned is exactly the same as just containing 2 distinct points. So these are the lines that are spanned by these. Well, here's 5 points. Here we have 5 points, and I've drawn every line that contains at least 2 of them. Those are the lines that are spanned by these points. If you have a collection of points in a higher dimensional space, every time there's 3 points that aren't contained in a line, then you draw the plane that contains those 3 points. And in some cases, just like here, there are 3 collinear points, so it's not the same as every pair of points gives you a distinct line. You may have many pairs that give the same line. It's also not the same. There's not really, for lines, this one is a refinement of the one below. For lines, the number of K-flats that contain at least, if a line contains at least T points and T is at least 2, then that line has to be spanned by that line is spanned by the set of points because there's at least 2 points that are contained in that line. For higher dimensional, for planes, say, if you have T collinear points, then any plane that contains that line is going to contain T points, but it's not necessarily spanned because these points are all collinear. So there's some subtleties that arise in the higher dimensional case. So for a K-flat is determined by K plus 1 points. If you take K plus 1 points that aren't collinear or that aren't contained in a lower dimensional space, then those give you a unique K-flat. So this is order n to the K plus 1 is the largest number of K-flats that could possibly be spanned. So this is a reasonably good theorem. Fk is at least this number. Yes, thank you for that. So either a single, so in 3 dimensions we're saying either a single plane contains at least some constant fraction of the points, or the number of planes is cubic. And you might want to say, so one observation is that theorem 2 implies that theorem 3 holds for any C sub 1 less than 1 and a suitable C1 prime. Right, so if we think about just the version of this theorem that deals with lines, it's strictly weaker than theorem 2. Or at least, it's basically, if we put C, you can put any CK less than 1 here. And then we're saying either a single line contains 99% of the points, or we have quadratically many lines. Well, that if we put 0.99 m in for G here, we've got m times 0.01 m times some constant So that's quadratic, this is a quadratic lower bound. So now the question is, you know, when you see this theorem, maybe the first question that comes to mind is, can we always take CK to be anything less than 1? Answer here is no. And so here's a key example. There's a we have the P is contained in the union of two skew lines. So skew means that they don't intersect. So here's the picture saying this line here is in front of that line behind. That's why I have a break. These are two lines in space like this. And this one has A points on it, so let's say L1 intersect P is equal to A. And this one has, well, M minus A points. So L2 intersect P is M minus A. Well, let's calculate first the number of lines that this spans. We know from Becks Theorem that it should span at least order M minus A times A. But let's do it more exactly. Does anyone want to help? Right, 2 plus A times M minus A. Right, you take a line on this line, you take a point on this line, a point on that line, that gives you one unique line, and then you have the two lines that you started out with. So 2 plus A minus M minus A. And how about planes? A choose 2. Yeah, right. Yes. Sangil has it. It's M. It's A plus M minus A, which is equal to M. And the way that you look at this is, well, you have to have 3 points to span a plane. As soon as you have 2 points, well, as soon as you choose 2 points on one of these lines, that entire line is going to be contained in the plane that you're spanning. So what you do, you choose one of the lines and one of the points on the other line. That gives you a collection of planes. And now you choose the other line and one of the points on the original line. That gives you a collection of planes, and now you're done. You've covered all triples. Well, that's rather unfortunate, in some sense, for our hope that we could get we really wanted a cubic lower bound here, not a linear lower bound. So, and we could have, in the case that A is exactly M over 2, we may not have more than half M plus 1 points on any plane. So this immediately implies that theorem 3 does not hold true. With CK equals 1/2. So now this is the state of the art as of 1983. Is for every k, there exists some constant c sub k, which in Beck's proof was depending. It's something like e to the minus, maybe e to the minus order k. So he's using an inductive proof where you lose a multiplicative factor at each dimension. So it's actually a pretty good state. We don't know what this constant CK is. We know it can't be 1. And there's some bound coming from Becks Theorem. Now, a few years ago, in the context of working on some other problem, I found a maybe more complicated, but also more satisfying generalization of Theorem 2. To say exactly what this is, I need to introduce a little bit of notation. The problem that we ran into here is that this pair of lines is acting, the span of these points is 3-dimensional, but in terms of the lattice of flats that are coming out of it, it looks a little bit more like a 2-dimensional set. Not exactly, but we're really not getting the number of planes that we would hope to get from a genuinely 3-dimensional set.
Is there any guess about the asymptotic of CK?
Well, I can tell you exactly what the best possible value of CK is, but later in the talk. So what I do is introduce this statistic, or this essential dimension, which is going to capture, for this set of points, it'll be 2. And so it gives the more proper combinatorial behavior here. And what this is the minimum over partitions. So rho is going to range over partitions where every part has at least 2 points. I'll write that down. Minimum over partitions rho of the sum over the parts Q and rho of the dimension of the span of Q. And here, rho is a partition with every part having size at least 2. It's a partition of P.
The number of parts is unlimited?
Number of parts is unlimited, yeah. But as you get more, because you're taking the minimum, you want to group the points together as much as you can. And yeah, one observation is that this is bounded above by the dimension of the span of P. Can you see why this is?
Well, it's partitioned into one member.
Exactly, right. So we're taking a minimum over partitions, and always living in this partition is we're going to put all of our points into one bucket, and in that case, we just get the dimension of the span of the point set. As long as you have 2 points. In the case that you don't have 2 points, these whole problems are not very meaningful, so I'll pretend like it can't happen. Yeah. So the other piece of notation, here, in Theorem 2, we have this G, which is the maximum number of points on a line. For the higher dimensional version, I want the higher dimensional analog to G. And this is going to be G sub K, which is the maximum over subsets of P, such that the essential dimension of that subset is at most, let me call it I, G sub I. At most I, of the cardinality of Q. So in the case that I is equal to 1, well, we're taking the maximum over subsets of P, whose essential dimension is 1. The only way that you can have an essential dimension of 1 is if all the points are collinear. As soon as you have, you're always taking the span of a collection of points that's at least 2 points, so that each term here is at least 1, and you're always going to have at least one term. So the essential dimension is bounded below by 1. So G sub 1 is the same thing as G in that case, but now in G sub 2, we're taking the maximum number of points that are contained in a plane or the union of two lines. See, because here we kind of wanted this guy to be a two-dimensional set, and we've got the dimension of the span is 3, but the essential dimension is 2. Because we can partition the points into the points that lie on each line, and then we get 1 plus 1 in this sum. So what don't know if it's clear from the definition. I'm just going to special case this, so for simplicity and notation, I'll say that G sub 0 is always 0. And I just wanted to keep things neat, and then this is going to clearly increase monotonically, because every time you increase the dimension, you're going to be able to add at least 1 point to what you had before until you've containing the entire point set. So G0 is always 0, G1 is the maximum number of points contained in our line, G2, maximum number of points contained in either the union of two lines or a plane. And this is always going to increase monotonically until we get up to G sub k of p, G sub the essential dimension of p, where we now can take the entire point set. And you can continue to increase the argument here, but once you have the whole point set, it's done. No, there's no way to increase it anymore. So here's theorem 4. This is this is my theorem. So what do we get? We get f sub k is equal to bounded below by some constant times the product from I is equal to 0 to k of n minus g I. So if we take I is equal to 1, then we get n minus g0 is n. I'm sorry, I'm trying to switch to m for points, because many of the papers in this literature have used always m for points and n for lines, or n for the geometric object. And I'm just trying to switch my habit to be more consistent with what other people do. All right, so m minus g. So in the case that gi is 1, in the case that this is for all k at least 1, and then this constant here depends on k. In the case that k is equal to 1, this is exactly Beck's theorem, and in the higher dimensional cases, it's actually a genuine strengthening of theorem 3. It's a little complicated though with this essential dimension and the g sub i's, and this wasn't a conjecture or anything. This was more of a lemma that I came up with in order to prove some other things. The real motivation for this was a conjecture of Purdy. So this is a corollary, and it was conjectured by Purdy. This is either n minus gk is very small. Well, let me say, for all k exists a constant c sub k such that either n minus G sub k is at most C sub k, or f of k is more than f of k minus 1. And actually, this is not only a lower bound, but it's a tight lower bound, which is not. The upper bound for lines is completely trivial. It's not really trivial in this case, but the lower bound is definitely the more interesting part. So, but we need the upper bound also for this theorem. And the point here is that, if the last term here is large enough, well, then we get a lower bound on the number of Kflats that includes that last term, which is at least C sub k. We have an upper bound on the number of k minus 1 flats with a different constant leading, but it doesn't include that constant C sub k. And so the lower bound on f of k is going to be greater than the upper bound of f of k minus 1, and so this is really an immediate corollary to that theorem. And this conjecture was open even in 3 dimensions since 1980s or so, late 1980s. And maybe this C sub k has, I found examples that show that this can't be, for example, 1. I don't know what the value is for this, but it can't be 1.
So I'm saying that this was open until 80, or did you say that
this was open from the late 80s until 2016, yeah. Not like a very famous problem, but it was in a couple of books, and so it's not, people looked at it, at least. It wasn't completely ignored, yeah?
What was the subscript setup right here?
Here.
Over there?
Where?
Setup. In theorem 4.
Theorem 4.
Subscript setup.
This is k. K, so for all k greater than 1, so this is the dimension of we're looking at the number of Kflats. Here. Oh, theta. Yeah, you said theta. It's also k. So the constants depend on k. That's all I would say. There's an upper. So it's for all k greater than 1, there exists constant C1, C2, such that f of k is at least C1 times this product and at most C2 times this product. And those constants C1 and C2 both depend on k. Yeah, there's 2 constants hidden in the theta notation, and they both depend on k. And the dependence is an inductive proof, and so the dependence is kind of exponential. Yep. So this part, as far as the constants, I don't know how tight anything is here. Here's another corollary, which I didn't notice immediately, but later, is that theorem 3 holds for all k exists for all ck less than 1/2 exists ck prime, so that theorem 3 holds. So we know that, so theorem 3 is, here we can always take ck to be 1/2, or anything less than 1/2. We know we can't take it to be 1/2 already for C2, and we know that C1 we can take to be anything less than 1. So this is for all k, this is the optimal, this is as good as you can hope for ck. And how does this work? Well, it's pretty much immediate from theorem 4 that either there's a set of essential dimension k. So if you replace a k-flat with a set of essential dimension k in this theorem, then you can take ck to be 1, anything less than 1. You can't take 1, but you could take anything less. Then you say that, well, no set of essential dimension k contains 99% of the points. Well, that means that all of these terms are some positive fraction of m. So you're going to get as many, you're going to get constant m to the k plus 1 Kflats. And then the second part of the argument is to realize that if you have a set of essential dimension k that contains, say, n points, then you have to have a Kflat that contains half n points. And this is just some fairly straightforward case analysis. So this immediately gives, well, immediately in a page gives the type value for C sub k in Beck's theorem. So I only have 15 minutes left. I was going to show a proof of just the lower bound in 3 dimensions. Do you want to see the proof of the lower bound in 3 dimensions, or do you want to see more applications and some other problems about point hyperplane incidences? Because I can't do both. Maybe I'll do the more problems. Okay. Okay. More problems is good. The proof is like, really it's a bit complicated and delicate, but it's not using any high-tech machinery. What we're doing is we just are using projection together with semi-Trotter and Beck's theorem, and we find a good set of points where we know we can look at the projection of the rest of the points, and we know that there have to be many planes that contain this point and many planes that contain this point, and we add up everything, and so it's a question of identifying the right cases, and I mean, there's some nice clever arguments, but there's no it's not like we're using polynomial method or some results proved somewhere else. It's just a very careful argument, combinatorial argument using symmetry and Trotter together with projections. But, all right, so that's basically it for generalizations of Beck's theorem. I already erased symmetry and Trotter. Let me write it down again real quick. Symmetry and Trotter is the number of, there are two expressions. One of the equivalent expressions is that the number of lines that contain at least 2 points is bounded above. Let's get the inequalities right. Bounded above by m squared over t cubed plus m over t. Now, in general, we would like to say, given a set of points, how many t-rich planes are there relative to that set of points? And we're not without requiring anything about the planes, there's something very trivial that happens, which is, suppose that we have a line that contains t points in, say, R3. Now, there are infinitely many planes that contain that line, and they all contain t points. And it's a similar thing if you're looking at an upper bound on the number of incidences between points and lines. Again, you could put you have n points, put them all on a line, have all your planes contain that, and you get n times n incidences. But you know that every pair of a point in a line contributes at most 1 incidence, so this is a completely trivial bound. And so without making some additional assumptions about the planes that you're going to count, you cannot do any non-trivial incidence bounds. And there have been a number of different bounds that have been proved. There are a number of different things that have been considered. The first one I want to talk about is a theorem of Elekes and Toth And I'm also going to give myself credit, but I'll tell you exactly what I did. The basic theorem is due to Allegash and Toff. This work led to some improvement to the theorem, so that the form that I'm going to write is the improved version. Okay, so the number of, now I'll use a term that I haven't defined yet. I'll go ahead and define it after writing the theorem. Alpha degenerate. T-rich. K-flats. So we have some points at P in RD. D doesn't really play any role here. And the number of points is M. So the number of alpha degenerate, which I haven't defined yet, T-rich K-flats, is at most constant times n to the d over k to the d plus 1 plus n to the d minus 1 over k to the d minus 1. Okay, let's not use d for these guys. How about, this should be k plus 1. And this is k plus 2. And this is k and k. And this is t. Okay, sorry about that. Maybe I should rewrite. Is this clear enough, or should I rewrite it? It's clear. It's okay. Alpha is a constant. Anything between, alpha is a constant between 0 and 1. And degenerate I'll define in a moment. So alpha degenerate means a K-flat is alpha degenerate if at most alpha fraction of the points y on a k minus 1 flat. So I think it's helpful to think about this theorem in terms of point plane incidences in 3 dimensions. This is M, yeah. Thank you very much. I managed to change all of the letters from what I had written down. And this is for all alpha between 0 and 1. Alpha and k. But not on M or T. Okay. So this is maybe easiest to think about in 3 dimensions. What you're saying is that if you count incidences between, of course the number of T-rich planes can be arbitrarily large, but if we require that we're only going to count those planes, so if you've got T points collinear, then we're going to only count those points that also have 1 minus alpha T points that are not also contained in that line. So every plane that you look at, it has some number of, it has, say, T points. And if we take, say, alpha to be 1/2, then maybe half T points on a single line, and then half T points somewhere else. And these are the only type of plane that we're going to count. And by restricting our count in this way, now we can get a non-trivial upper bound on the number of T-rich planes. And also, if you plug in k is equal to 1 here, then recover the semi-Inchato bound. So it is for lines, it gives semi-Inchato like you would hope. And for planes, we're getting a non-trivial and tight upper bound. And of course, we have to have some assumption, and the assumption that we're using here is the alpha degenerate. Now, T-rich means that it contains at least T points of P. So this is T-rich relative to P, and T-rich means contains at least T points of P. Is the statement clear here? So when Ellicott and Toth proved this theorem, they had exactly this theorem for k equals 2. So a kind of three-dimensional case where we're thinking about points and planes in 3 dimensions, they have exactly this theorem. And then for in higher dimensions, they had a upper bound on alpha that depended on the dimension. So you would always have, for all alpha between 0 and some ck, where ck is for C2, for example, is something much less than 1, and it's always going down to 0. So this is a similar kind of improvement as in Beck, except that we get to alpha all the way to 1. Now I can say very briefly what is the relationship between these problems is that actually the main theorem of Ellicott and Toth is that is the same upper bound on the number of incidences between what they called gamma saturated planes and points. Where gamma saturated, you'd say that a hyperplane is a K-flat is gamma saturated if it spans as many, if the points inside of it span as many k minus 1 flats as possible, up to some constant. So if it contains m, if you have, say, t points on a plane, it's going to be, you have t points on a 2-dimensional plane, would be saturated if it spans gamma times t squared lines inside the plane. Does that make sense? So then that theorem plus Beck's theorem immediately gives this theorem, because Beck's theorem says for each k, there's Beck's theorem says either a single k minus 1 flat contains most of the points on the k flat that we're looking at, or it's saturated, right? So we know that we have a upper bound on the, so Ellicott and Toth proved the upper bound on the number of incidences between saturated planes and points. And Beck's bound shows that if a plane is not degenerate, then it's saturated. Therefore, you get the same upper bound on the number of incidences between planes and non-degenerate, or between non-degenerate planes and points. If this is maybe a lot to say, but that's the connection there. So by improving this C sub k to 1/2, that immediately improves the upper bound on alpha here to 1/2. To get it to 1 is a little bit more work. What you have to do is show that you can't have too many, you can't have a lot of sets of points that have smaller, given some arbitrary set of points in a high dimensional space, you can't have a very large number of sets of points that have a very high essential dimension that are not also contained in where you don't also have a single hyperplane that contains a lot of points. So that's kind of, so to get it all the way to 1 here is a bit of extra work. Now there's an open problem related to this that I want to mention. So this bound is tight. And especially I want to focus on the second term here, and especially I want to focus on the case that we're talking about planes. So Elikeshentoff for k is equal to 2, we have the upper bound is order m to the 4 over t cubed plus m squared over t squared. M to the 3rd over, yes, thank you, Tuan. He's giving me a hint. All right. Now, as you get into higher dimensions, for applications, this term here it causes problems. This is kind of a trivial term, but it's also a somewhat painful term to have. And the construction that shows that it's tight is also kind of silly. What I'm going to do is show a head-on projection. So behind each of these points that I'm drawing here, there's a line of, let's say, t over 2 points. And so we just put them however you want, and you have n over t lines, m over t lines. And now we have m over t squared pairs. And there's a distinct t-rich plane. So these are lines going back into the board. And every pair of lines spans a plane. And every plane that is spanned is 1/2 degenerate, because it contains 2 lines of points with t over 2. So if you look at one of these planes, you've got t over 2 here, t over 2 here. And these are parallel lines. So it's alpha is 1/2 degenerate, t-rich, and we have m squared over t squared pairs. But what I would like to do is, this is really only giving, this construction really depends on having alpha as high as 1/2. If we can drive alpha down, you could easily have alpha to be, say, 1 over square root of m or something, or 1 over some power of m. And so I won't go into, but kind of the best that we could hope for, so this is a conjecture, would be m cubed over t fourth plus alpha m squared over t squared plus m over t. And I think that this would be good for applications, and it should be achievable. And we know that we can't completely remove this silly term, but if we could, by requiring if we're in a situation where our planes are less degenerate, we'd like to be able to take advantage of it. So I think this is a nice question, would be to get this dependence on alpha. And then similarly, there would be also a higher dimensional version. Okay, sorry I've gone over time.
Thank you. Any questions?
problems you use combinatorial tools. Like,
Yeah.
Is it expected that the improvements can be made only using such a tool, or do you think some tools from polynomial method?
So these problems I've been talking about, where you're looking at kind of the most degenerate cases, where what happens when your points are in some very degenerate situation, where using really combinatorial tools. There are many problems where if you forbid, say, a KST where S and T are constant, there have been a lot of recent results, and this is using the polynomial partitioning method that was introduced by Guth and Katz. And there have been a lot of, and so that's a much more recent development that uses a lot more algebra and a lot more algebraic geometry and a lot more real algebraic geometry than what I've been talking about is really all the results I mentioned today. The proofs are quite elementary. And so when you look at this alpha here, I'm not so sure whether it could be done using kind of purely combinatorial tools as in the results that I mentioned today. I don't know if it can be approached using the tools that I mentioned today, or it may be a combination of tools from this as well as, I mean, you have there's an entire toolkit that's been developed in the last 10 years, whereas most of these questions most of the results that I mentioned other than my own are predating that whole renaissance, starting from Guth and Katz's work on the distinct distances problem. So there are a lot more tools available, and I don't know for sure. For this particular problem, I'm not sure. I mean, there's another problem that I think maybe these purely combinatorial tools had a better shot at, but I didn't get to it.
Any other questions? Okay, if not, let's thank the speaker again. So next week